In this video, I will go over a summary, an overview of what the method of separation of variables looks like in Cartesian coordinate system. If you don't have the Cartesian coordinate system, but you're working with something else, the cylindrical or the spherical coordinate system, it will look the same, but of course, instead of x, y, z, you will have other coordinates. All right. So the goal here is to solve the Laplacian equation in an area where there is no charge density, and in the Cartesian coordinate system, I'm assuming that I'm working in 3 dimensions. The potential needs to be a function of x, y, z. Now, in the Cartesian coordinate system, the Laplacian is the second partial derivative of potential with respect to x, and the same thing with respect to y, plus the same thing with respect to z is equal to 0. In the method of separation of variables, we make the assumption that the potential, which is a function of x, y, z, is a product of one function that depends only on x times one function that depends only on y times a function that depends only on z. Now what I will do, I will take this and I will plug it into the Laplacian for the Cartesian coordinate system. Now, because before I do that, because this first term is the second partial derivative with respect to x, the y function and the z function, they are constants as far as a derivative with respect to x is concerned, because they don't depend on x. So what I can do, I can take them out, and then I have the second partial derivative of the x function with respect to x. Something similar is true for the second term. This partial derivative is with respect to y, and only the middle, the y function, is the one that depends on y. The x function and the z functions, they have no dependence on y, so regarding this partial derivative, they are constants. So what I can do, I can take them out. And similarly, for that last term, I will have the x function times the y function times the second partial derivative of the z function with respect to z, and this needs to be equal to 0. Now in the next step, I will divide this left hand side and the right side, but of course that gives me 0. I will divide both sides with x, y, and z. And when I do that, the y and z functions cancel out, and at the end I will have 1 over my x function times the second partial derivative of that x function plus, here for the second term, I will have 1 over y times that partial derivative plus 1 over the z function times that second partial derivative. Now here I have a sum of 3 terms, and if you look at the first term, this function is dependent on x, and it's the same function here, so I have only x dependence everywhere on the first term. This second function depends entirely on y, and the 3rd function depends entirely on z. the only way that the sum of these three completely independent functions can be zero is if each one of them is equal to a constant. So 1 over the function x times the second partial derivative of that function with respect to x squared. This needs to be a constant c1. The same thing for the second term. And similarly for the last one. Now, I want to point out that here I had an equation that had partial derivatives. However, once I get to this point, this isn't only a function of x and this is a constant. So what I have really done by doing this separation of variables, I have actually transformed that partial differential equation to an ordinary one. These are derivatives, not partial derivatives. Alright, now I'm gonna rewrite this. I'm gonna move this denominator on the other side. So I have d squared of the function x over dx squared equals c1 times the function x. And something similar for the other ones. I will not write the same thing for the other ones. I'm gonna use this and I'm gonna show you, I'm gonna give you the overview of your approach just using that. Now, there are two possibilities. Either the constant c1 will be a positive number or it will be a negative number. Now, from experience, the more problems you solve, the easier it will become for you to see at this point whether it will be positive or negative. Now, okay, what happens then as you're learning how to do this? This is what you're gonna do. You're gonna try one. Let's say you're gonna try the positive one, and you will run into trouble because making the assumption that C1 is positive does not allow you to fit the boundary conditions. And remember, you will find the potential in a volume, but you have to satisfy the boundary conditions given by the problem. And if you make the assumption that C1 is positive and you cannot satisfy, no matter what you do, you cannot satisfy the boundary conditions with that, that means you made the wrong choice and you're gonna forget about that and you're gonna go and change your assumption for C1 and then you will say that C1 is negative, and hopefully this will allow you to satisfy your boundary conditions. Now I will show you what the solutions are in the two cases. If we make the assumption that C1 is positive, then I can write C1 as k squared, and my differential equations become as d squared x Now what I have here is that the second derivative of my function x, is equal to k squared times the same function x. Now, if you've taken differential equations, you may already know the answer to this. If you have not, I can tell you that a function that actually satisfies this is the e to the kx. If I take the first derivative of e to the kx, I get a k to the front, and then the second derivative of that will give me k squared times ekx, which is my original function. So I get k squared times my function, which is what I have here. So the general, now the same thing is true, okay, for e to the minus kx, because the second derivative will have two minus signs and it will give you a plus. This means the general solution to this differential equation is this one: a times e to the kx plus b to the e minus kx. If you're not convinced with this, do the following: take the first derivative with respect to x, and then take the second derivative with respect to x and plug it into your differential equation, and you will see that the left side is equal to the right side. Since I have satisfied the differential equation, this is the solution to this differential equation. Now, there are some things that we have not specified yet. Yeah, I found the solution, but I don't know what is a and b. Well, this is where the boundary conditions come into play. Whatever boundary conditions you're given from the problem, those will determine what is a and b, and also the k. Now, I'm gonna examine the other case where c1 is a negative number. In that case, I will write c1 as minus k squared, and my differential equation becomes minus k squared times the function x. Again, if you've taken differential equations, then you already know what's the answer to this. But I can, this form is telling me that the second derivative of the function I'm looking for is minus k squared. And I know when I take the derivative of sine, I get a cosine. And when I take the derivative of cosine, I get minus the sine. So the second derivative of sine gives me minus sine. And this is telling me that the solution to this differential equation will need to be of the form sine kx. And of course, the same thing is true with cosine kx. It does give you minus, the second derivative does give you minus cosine kx. So the general solution to this differential equation is a times sine kx plus b times cosine kx, and this is the function that I'm looking for. And similarly for a and b and k, here these terms will be determined for every problem using the boundary conditions. And again, this is, okay, I do want to let you know, this is extremely useful somehow, somewhere, to take notes on your notebook and be able to refer back to it, because you're going to be doing this a lot. And you don't have to really remember, just once you see your differential equation, that it's k squared x, then hopefully you remember that the e to the kx, this is what can satisfy that differential equation. In case where you have the minus k squared, then just remember sine and cosine are the two functions that satisfy this differential equation. And again, going back here, whether you're going to make the choice for positive or negative, the more problems you solve, the easier it will be for you to see how you need to proceed. And okay, so that was a discussion only for the x function. You will do exactly the same thing in the y, and if you're working in 3 dimensions, in the z as well. Now, I showed you here that by doing this, you get your function for the x function. And then by solving the other three differential equations, you're gonna have the y function and the z function. And once you have them, at the end, if you want to write your solution for potential, then you're gonna use those three to in order to go back. Where is it? And see. All right, here it is. You're gonna go back and put everything together and say, okay, now finally I have the solution for potential as a function of x, y, and z.